Welcome to MRL. In this learning session, we'll study about chord, properties of chord and theorems related to chords. Now, what is a chord? A chord is a line segment joining any 2 points of a circle. And if you see here, A and B are 2 points on the circumference of a circle. AB is joined and therefore AB is a chord. Infinite chords can be drawn in a circle. A diameter is also a chord. Rather, a diameter is the longest chord. A chord which passes the center of the circle is known as diameter, or the longest chord of a circle is known as diameter. Infinite diameters can be drawn as infinite chords can be drawn in a circle. So remember, diameter is the longest chord, or a chord that passes the center of the circle is known as diameter, and that is what is about a chord. Now let us proceed further. Now the different properties of chords. The length of chords increase as the distance of the chord from the center decreases. So if you see here, the chord AB, the length of AB is smaller than length of CD because the distance of AB from the center is greater. Therefore, the length of the chords increase as the distance of the chord from the center decreases. So D2 is greater than D1 here, and therefore CD is greater than AB. CD is greater than AB. If chords are congruent, then the corresponding arcs are congruent. If you have two chords AB and CD, they are equal. AB and CD are equal, and the arc is APB here and the arc is CQD here. So these two arcs are also congruent. That means if chords are congruent, then their corresponding arcs are also congruent. That is, arc APB is equal to arc CQD. Now, congruent chords obtain equal central angles. If the chords AB and CD are equal, then the angle which they subtend at the center, that is angle AOB and angle DOC, are equal. They subtend equal angles at the center. The perpendicular from the center of a circle to a chord bisects the chord. So if you have a chord AB, a line joining a perpendicular drawn from the center of a circle to the chord bisects the chord. OC is perpendicular to AB, AC is equal to BC. Remember that a perpendicular drawn from the center of a circle to a chord bisects the chord, a very important property. The line joining the center of a circle to the midpoint of a chord is perpendicular to the chord. That means if you have a chord AB, if the M is the midpoint of AB, if I join M to the center of the circle, then OM is perpendicular to AB, a very important property again. Now coming to the next important property, equal chords of a circle are equidistant from the center. If chords AB and CD are equal, then the perpendicular distance from the center, that is OM and ON, are equal. So remember that. Now chords of a circle which are equidistant from the center are equal. So if there are two chords which are equidistant from the center, then the two chords are equal. That means that if the distance OM is equal to ON, then the chord AB is equal to chord CD. So that is what you have to remember. Now the segment of a chord. A point on a chord divides it into two segments. Please understand this. A point on a chord divides it into two segments. Now the segments formed are by internal division or external division. The segments formed when internally divided are AR and RB. Now if you see here, R is a point on the chord AB and it is internal division, therefore, and the internal division and the internally divided segments are AR and RB. Now the point S is also on the chord AB and it is externally divided, and the segments are SA and SB. So remember this, that a point on a chord divides it into two segments. It can be internally divided or externally divided, a very important property again. Now angles in the alternate segment is a very important property again. A chord and a tangent to a circle form alternate segments. A chord and a tangent to a circle form alternate segments. The angle formed by a chord and tangent is angle BAQ. The angle formed in the segment by the chord, angle ANB, is the angle in the alternate segment with reference to the angle BAQ. Similarly, the angle ANB is the angle in the alternate segment with reference to the angle formed by the tangent and the chord, angle BAP. And please remember, angle BAQ is equal to angle ANB and angle BAP is equal to angle ANB. Now let me explain this with the help of the diagram here. Now we have a circle here. AB is the chord and PAQ is the tangent, A is the point of contact. Now the angle between the chord and the tangent is angle BAQ the angle in the alternate segment is angle AMB. The angle BAQ is equal to angle AMB. Remember that. And also the chord AB forms another angle with a tangent, and that is BAP. And the angle in the alternate segment is BNANB or BNA, and angle BAP is equal to angle ANB, a very important property which you have to remember. Therefore, remember the angles between a chord and a tangent at the point of contact are respectively equal to the angles in the alternate segment. On circles related to the properties of chords. The first theorem, it states that equal chords of a circle subtend equal angles at the center. The meaning of this is, there are two chords AB and CD and they are of equal length. Now we have to prove that the angles which these two chords AB and CD subtend at the center, that is angle AOB subtended by the chord AB and angle COD subtended by the chord CD, are equal. So let us understand how to prove it. Now we are given AB and CD are equal chords, AB and CD are equal chords, and we have to prove that these two equal chords subtend equal angles at the center. That means we have to prove that angle AOB is equal to angle COD. Now let us consider these two triangles here. In triangle AOB, that is triangle AOB and triangle COD. Now OA is OA and OD are radii, OA and OD, OA and OC, OA and OC are radii, so also OB and OD are radii. And AB and CD are equal, which is given to us because the chords are equal. Therefore, by triple S congruency criteria, these two triangles are congruent. If two triangles are congruent, then the corresponding angles are equal. Therefore, angle AOB is equal to angle COD. So, very simple proof of this particular property of chords. And also you should understand that if the angle subtended by arc, so you have arc AB here and arc CD here. So this chord has an arc AB and this chord has an arc CD. That means arc AB and arc CD, if they are congruent, then they subtend congruent angles at the center. The converse of that, if the angles subtended by the arcs at the center are equal, then the arcs are congruent. If the arcs are congruent, then they subtend congruent angles at the center. A very important relation which you have to remember, which is again based on this particular theorem. So this is what is the first theorem, that equal chords of a circle subtend equal angles at the center. Now this theorem is a converse of the theorem which we have just learnt, that the theorem states if the angles subtended by the chords at the center of a circle are equal, then the chords are equal. That means we are given the angle subtended by the chord AB at the center is angle AOB, angle subtended by the chord CD at the center is angle COD. If angle AOB and angle COD are equal, then the two chords AB and CD are equal. That is what we have to prove. So let us understand the proof of this. Now we are given AB and CD are two chords. Angle AOB and angle COD are the angles subtended by the chords AB and CD. Now we have to prove that chord AB and chord CD are equal. Now let us consider these two triangles here. Let us see these two triangles here. In triangle AOB and triangle COD, OA is equal to OC, OB is equal to OD. OA is equal to OC and OB is equal to OD. They are the radii of the circle. And also angle AOB is equal to angle COD is given to us. Therefore, by side angle side congruency criteria, these two triangles are congruent, and if two triangles are congruent, then the corresponding sides are equal, and therefore AB is equal to CD. Therefore, chord AB is equal to chord CD. That is what is the proof of the theorem. So therefore, remember the theorem: if the angles subtended by the chords at the center of a circle are equal, then the chords are also equal. Remember that. In this theorem, the statement given is the perpendicular from the center of a circle to a chord bisects the chord. Now let us understand the meaning of this. See, we are given a circle with center O, AB is a chord, OP is perpendicular to AB. Now we have to prove that the perpendicular OP bisects the chord AB, that is AP is equal to PB. Let us understand the proof of this. Now given circle with center O, we are given a circle with center O, AB is a chord, OP is perpendicular to AB. Now we have to prove that AP and PB are equal, or OP bisects the chord AB. Now join OA, construction is join OA and OB. When we join OA and OB, we get two triangles AOP and BOP. In triangle AOP and triangle BOP, OA is equal to OB because they are radius of the same circle, and angle OPA is 90 degrees, OPB is 90 degrees, and OP is common to both. Therefore, by RHS congruency criteria, right, that is right angle, hypotenuse and side, right angle, hypotenuse and side, and the side, the two triangles AOP and triangle BOP are congruent. If two triangles are congruent, corresponding sides are equal, therefore AP is equal to PB. That proves that in a circle with center O, if there is a chord AB, if you draw a perpendicular OP to the chord from the center of the circle, then it divides the chord into two equal parts. That means AP is equal to PB, and that is what is the proof of this particular theorem. Now let us proceed with the next theorem. Now this theorem states that the line joining the center of a circle to the midpoint of a chord is perpendicular to the chord. The line joining the center of a circle to the midpoint of a chord is perpendicular to the chord. That means what is the meaning of this? We are given a circle with center O, AB is a chord, P is the midpoint of AB, O is the center of the circle. When we join OP, that means when P and O are joined, then we have to prove that OP is perpendicular to AB. So let us see how to prove it. Now given circle with center O, AB is a chord, P is the midpoint of AB, and OP is joined. Now we have to prove that OP is perpendicular to AB. Now it is enough for us to prove that angle OPA is equal to 90 degrees. That makes OP perpendicular to AB. Now join OA and OB, and we have two triangles here, triangle AOP and triangle BOP. In triangle AOP and triangle BOP, OA is equal to OB radius, and PA or AP is equal to BP because P is the center and OP is common to both. By triple S congruency criteria, triangle AOP and triangle BOP are congruent. If two triangles are congruent, then the corresponding angles are equal. Therefore, angle OPA is equal to angle OPB. OPA is equal to angle OPB. But we see that APB is a straight line. Angle APB is equal to 180 degrees. That is, angle OPA plus angle OPB is equal to 180 degrees. But angle OPA plus angle OPB are equal. Therefore, 2 times angle OPA is equal to 180 degrees, or angle OPA is equal to 90 degrees, and therefore OP is perpendicular to AB. That is what is the proof of this theorem, and please try to remember that. For circle. Now in this theorem, we have to prove that equal chords of a circle are equidistant from the center. What is the meaning of that? We are given a circle with center O, and the two chords AB and CD are equal. Now we have to prove that the distance OP and OQ are equal. That means the two chords are equidistant from the center. Now let us see how to prove it. Now given circle with center O, AB and CD are equal chords. OP is perpendicular to AB and OQ is perpendicular to CD. OP is perpendicular to AB and OQ is perpendicular to CD because we have to always find the perpendicular distance of the two chords from the center. Now let us assume that AP and CQ is equal to L because chord AB is equal to chord CD. Half of chord AB and half of chord of CD are equal because P is the midpoint of AB, because when we draw a perpendicular OP to AB, it bisects the chord AB, and so also OQ is perpendicular to CD, it bisects the chord CD. The chord AB and chord CD are equal, therefore half of chord AB and half of chord of CD are also equal, therefore AP is equal to CQ is equal to L. So please remember that. Now to prove this, join OA and OC. When we join OA and OC, we get two triangles, triangle AOP and triangle COQ. In triangle AOP and triangle COQ, OA is equal to OC because they are radii. Angle OPA and angle OQC is equal to 90 degrees. That is because OP is perpendicular to AB and OQ is perpendicular to CD. And also AP is equal to CQ, just we have discussed that. Therefore, in triangle AOP and triangle COQ, we have by RHS congruency, the two triangles are congruent. If two triangles are congruent, then the corresponding sides are equal. Therefore, OP is equal to OQ. Therefore, the perpendicular distance of the two chords AB and CD are equal. That proves the theorem that equal chords of a circle are equidistant from the center. A very simple proof. Try to remember that. Now the next theorem. Now the next theorem, it states that chords equidistant from the center of a circle are equal in length. Now the theorem is very simple. We are given a circle with center O, and there are two chords AB and CD at equal distance from the center. That means OP is equal to OQ. Now we have to prove that the chord AB and chord CD are equal in length. Now let us see how to prove it. Now given circle with center O, we are given circle with center O, AB and CD are two chords from the center and they are equidistant from the center. That means OP is equal to OQ. Now we have to prove that chord AB and chord CD are equal. Now join OA and OC. Now in triangle AOP and triangle COQ, OA is equal to OC because they are radii, and OP is equal to OQ, which is given to us, and that is the perpendicular distance, and the angle APO and OQC are equal to 90 degrees because OP is drawn perpendicular to AB and OQ is drawn perpendicular to CD. They are the perpendicular distances, and therefore by RHS congruency criteria, we have triangle AOP and triangle COQ are congruent, and because the two triangles are congruent, their corresponding sides are equal. Therefore AP is equal to CQ. Now we know that if AP is equal to CQ, P is the midpoint of AB, Q is the midpoint of CD. If I take 2 times AP, then that becomes a chord AB. If I take 2 times CQ, that becomes chord CD. Therefore AP plus PB is AB and CQ plus QD is CD, because P is the midpoint of AB. As we know, the perpendicular drawn from the center to a chord bisects the chord. Therefore AP plus PB is equal to AB and Q is the midpoint of CD. Therefore CQ plus QD is equal to CD. So that is what is the proof, because in this theorem we have proved that AP is equal to CQ, double of AP is AB, double of CQ is equal to CD. Therefore AB is equal to CD, and that is the proof of this theorem. So these are important properties of chords, and the proof of those properties in the form of theorems. If we have learned them in different parts, please go through all the parts, try to remember the properties, and it's very important for us to remember the properties of circles and the properties of chords and the various terms which are related to circle and the chords. So by that knowledge we can understand these theorems very easily. So please remember and note down these in a book for your future reference.